Now, just before I begin, I would like to apologise if the video freezes, because I'm having issues with my capture software at the moment, so it's kind of up in the air whether it will freeze or not. So I've put some simulation video on YouTube for you. I'll leave a link down in the description if you want to actually see the video for yourself. It's just a 10-hour simulation video. But onto the video. Everyone and their cat knows these days the very basics of how a computer operates. You have the bit that is 1 or 0, so it holds two values. The more bits, the more different values you can hold. For example, 64 bits can hold roughly 18 quintillion different values, and that's an 18 with 18 more zeros behind it. For reference, 32 bits can hold only 4 billion values, which is 4 with 9 zeros. But quantum computing takes almost all of this and throws it in the bin. So without further ado, I'm Ronnie from Team RGBritishTech, and I'm here to explain to you just what quantum computing is all about. To understand how it all works, you need a very, very basic understanding of quantum mechanics. All you really need to know is a couple of qualities of subatomic particles. Firstly, subatomic particles that haven't been observed are in a superposition of states. A superposition is where a particle is in multiple states at once because it hasn't been observed. It's like the saying that if you leave a room with a table in, is the table still there when you leave? Now the answer is the table could both be there and not there at the same time because of superpositions. But that's only for the sake of this scenario because, of course, tables are big and particles like photons are very small, so tables are being constantly observed by like microorganisms, but particles aren't being observed by microorganisms because they're too small to observe. Not to say that they have eyes to see, but observation doesn't have to be just eyes. It can be anything. Anything that a living being can do to tamper with the state of something, or to know the state of something. Now, the superposition quality means that quantum particles can hold multiple values for data at the same time. Compared to regular bits, they can only hold one value at a time, whereas they can still hold a lot of data in a small amount of bits. Quantum particles can hold the same amount of data as a large number of bits in a very small number of qubits, which is quantum bits. Now, a quantum bit, or qubit, is a particle that is used to hold data. The problem is, it is very difficult to read qubits without collapsing the superposition. In fact, we don't have any efficient methods of doing so, and it's incredibly difficult to store qubits for any extended amount of time. This is due to a phenomenon called quantum tunneling. Put simply, it is where a particle may randomly pass through a barrier that it not normally can pass through. This means qubits can escape and leave gaps in potentially important data. Some means of temporary storage using high-powered magnets have been developed. However, as many of you will know, magnets have a tendency to tamper with data, especially in hard drives. Now, when a particle is observed, the superposition collapses into one state. Back to the table analogy, when you walk back into the room, the table assumes its most likely state. For this scenario, its most likely state is that it is back in the room in the exact same place it was when you left. So if a hacker tries to intercept your data mid-transfer, with quantum computing the data will be unreadable, because when they try to intercept it, the superposition collapses, and it's worthless to them. That makes quantum computers extremely secure. Now, a quantum bit, or qubit, is very easy to create because it's to do with the spin of a particle. Spin is a fundamental quantity of a particle, and usually it can be up or down, and that gives the 1 or 0. So if it's spin up, it's a 1, and if it's spin down, it's a 0. It costs more energy to make it spin 1, and it costs no energy to leave it at spin 0. So you have to put in energy to change its spin to spin 1. Quantum computers are incredibly, unfathomably fast in comparison to regular computers. There is a very, very simple formula to understand how bits are scaled with qubits in terms of storage. If you imagine the number of qubits as x and the number of bits as y, then 2 to the power of x equals y. So for example, if you have 64 qubits, that can hold as much data as 18 quintillion bits, or 2 to the power of 18 quintillion. We already know that 2 to the power of 64 is 18 quintillion. So with 64 regular bits, you can hold 18 quintillion values. But with 18 quintillion bits, you can hold an unfathomably amount of values. If that was worded wrong, I apologise. One of the most well-known qubit values is 2 to the power of 300. Because if you have 300 qubits, the amount of data you can store in equivalent to regular bits is equal to the number of particles in the observable universe. This means wondrous things because it says that in theory our computers can become so small, smaller than a tic-tac, and still hold more data than there are particles in the observable universe. However, don't go thinking that they are faster in every single case. In fact, each process will probably take more time than a standard computer because you have to change the particle states so that they are actually readable. For specific calculations, the number of processes is exponentially smaller than that of a standard computer. So it is not that you shorten the time taken to do one process, but because there are such fewer processes, the whole calculation or task is much quicker than a standard computer. Essentially, it's not worth using a quantum machine for web browsing or general office work, but for specific calculations and difficult tasks that require a lot of compute power, like simulations, quantum computers suit the job incredibly. They are basically the future for research purposes and for scientific calculations, like at CERN or the LIGO Institute. Who knows, that maybe one day quantum computers will become affordable enough to be consumer-grade devices. The computer itself wouldn't need the whole 300 qubits to match a normal phone. In fact, it would only need 6 qubits to match a 64-bit system. But let's say it's an 8-qubit system that is embedded in a sheet of incredibly durable glass with the right lighting for an LCD. What you now have is essentially a near see-through device. It will be also easy to implement this device into some sort of malleable plastic screen so you can have a bendy phone that is much less prone to damage. So for instance, if you drop it, it won't shatter like a regular phone. If you drop that from a decent height, it's going to shatter. But if you drop or if you drops bendy plastic from a very high height, it's not going to shatter. It might chip, or it might leave a couple of scratches, but it won't shatter. There are so many more potential uses for a quantum machine, and so many unthought of ones that will potentially be, thought of in the future. When we finally discover or develop an efficient way to use quantum machines and maintain them, as well as store qubits effectively for a long amount of time, and prevent the superposition from collapsing when we observe them, the rate of development of many other new forms of technology will rapidly increase, potentially even exponentially increasing. Thank you for watching. Please make sure to leave a like so that the channel can grow, and subscribe so that you don't miss any content from us in the future. Also, please make sure to leave a comment in the comment section, as we are always looking for new ideas to add to our list. I'm Ronnie from Team RGBritishTech. Until next time.